Okay, next I want to discuss properties of Euler function. Properties of Euler function. So it's a really important gadget in number theory and group theory everywhere. It appears everywhere. So let's discuss some of its properties. So where shall I start? Okay, let's just start where we finished. So let's start with theorem of Euler. So theorem due to Euler. So we have two numbers, a and m are positive integers and they are co-prime. Then then not enough space, then m divides a power phi of m minus 1. So this is this fundamental congruence. Also, when you use notation of congruences, you will say a power phi of m is congruent to 1 modulo m. So that's a very important, very beautiful observation, and the proof is, of course, very simple for us. So proof is this kind of basic application of Lagrange theorem. So you take this z over mz times, and this is a group, let me call it G. So the order of G is given by the Euler function of M. And we know that there is this class of A is an element in G because they are co-prime. And then by Lagrange theorem, A power phi of M is equal to 1. But of course, that just implies that A power phi of M minus 1 is divisible by m, and that's the end of the proof. So, of course, one can prove it without quoting Lagrange theorem from group theory, and basically you will repeat this proof of Lagrange theorem for a billion groups, which was in the first homework. So that's how one can do it elementary. But let me kind of assume you have seen it maybe before. And this has a corollary, so how shall I? Fermat's little theorem. So Fermat little theorem is the following very beautiful special case. So P is prime and P does not divide A, then P divides A power P minus 1 minus 1. And of course, this is just take M equal to P and you get it. Okay, so next question is how to compute the Euler function. So how to compute, how can we compute phi of m? And there are different strategies. There are at least kind of two proofs maybe which are very interesting. Let me discuss maybe the more advanced one, and then I will say a few words about the other. So first, I mean phi of p is pi minus 1, p minus 1. And that's because we already discussed it, right? All primes less than p, but greater or equal than 1, p minus 1 of them, all are coprime with p. And phi of p power n, these are just numbers, so not number of elements, n from 1 less than p power n, such that n and p power n are coprime. But p is prime, so being coprime with p, the same thing as not having common prime divisors. This is, of course, the same thing as number of elements from 1 to p power n, such that n and p are coprime. And that's very simple to count, because how many of them are not coprime? Those divisible by p. And so the answer is p power n minus p power n minus 1. So these are all numbers p times something. And and this equals to p power n minus 1 times p minus 1. And we have seen already that phi of 8 equals to 8 minus 4 is 4, and that's a special case. So now we know how to compute our function for any power of a prime number. The question is how to compute it for any number. Okay, so very important theorem. So theorem. So for coprime n and m, we have phi of n m equals phi of n, phi of m. So for coprime numbers, this function is multiplicative. So people will say phi is multiplicative, but in number theory, in arithmetic, multiplicative has a different meaning. It's not just phi of any product of two numbers is a product. That's kind of almost never happens, but this is this property for coprime numbers. That's what's usually called a multiplicative function in number theory. And of course, we have seen already some examples like phi of 6 equals to phi of 2 times phi of 3. This one is 1, this is 2, and this is also 2. And we saw that here we had 1 and 5, here we have 1 and 2, here we have 1. And the question is how to prove it, and that doesn't look very obvious because, you know, that just doesn't look so obvious. If you look at particular elements here, how 5 here is related to there, that's not completely trivial. So we will prove a more advanced version of the theorem. So we will prove. So notice that this is the order of a certain group. So we have equality, the order of the group z over n mz times equals to the order of z of nz times the order times the order of the group z over mz times. And that gives a hint of how to prove this arithmetic statement, because maybe the groups are related in some way. So so suppose we have two groups G1, G2, and if they are finite, actually in any case, the order of G1 times G2 is always the product of orders. I mean, of course, you need to understand it kind of meaningfully if one of them is infinite. So if one of them is infinite, then if G1 or G2 is infinite, this is also infinite. If they're finite, this is equality of finite numbers. And that's just because for sets it's true. This is a set of pairs. That's why. And so it would be really nice if this thing is just isomorphic to product of two groups. So let's show that. And this will give a beautiful kind of proof of our theorem just looking at orders. So let's show that the group z over nmz times is isomorphic to z over nz times z over mz times. By the way, this is kind of a very interesting fact in math which happens all the time. So you have an identity for numbers, like for very elementary thing. And very often beautiful identities for numbers, polynomials or something like that, come from much more sophisticated statements about abstract mathematical objects like groups or vector spaces or whatever we will discuss later in the next quarter modules, by taking some invariance of them, like going from group to a number, its order is of course forgetting tons of information, but kind of this statement is so much more rich, fancy, and so on, but it implies this theorem. And this statement can be proven by constructing this, map, having these properties, And this, of course, gives a hint of why these two numbers are related. You just need to follow this construction. But in many cases, if you want to prove a statement like that, you need to first guess a fancier version of it. And a fancier version can be easier to prove because it's more clear what to do here. Because I just can look at these three groups and think how you can map something there and so on. Okay, so let's prove it. So proof is as follows. So let's take z over nmz times and send it to z over nz times z over mz times. So how to do that? There is one kind of naive idea, and it is as follows. So z over nz times z over mz times. So what can I do? So I can take my class A, and this is a class modulo nm. So this is a remainder modulo nm, but then of course I can look at it modulo n. So I send it to the pair consisting of A mod n, comma A mod m. So that's not clear. So you can do this with the remainders. So if you have a remainder modulo nm, you can look at it modulo n. And we just discussed it. It's because the subgroup nmz is contained inside nz. You can even think of it as this universal property of quotients. We had this example, z over 6z is mapped to z over 2z or z over 6z. So one can do that. And the question is whether it is indeed a homomorphism and whether it lands here. So, so first let's see that. So this is what I will call f. So first thing to check is that actually f lands there. So what I mean that these two numbers are actually invertible. And indeed, so if so we know that A is coprime with nm. So this is simpler to think in terms of A and common factors. So this means that there does not exist a prime P. P is always a prime, P prime, such that P divides A and P divides nm. But n and m are coprime, and this is a prime number, so this implies, this is of course equivalent to there doesn't exist P prime, or at least this implies, such that P divides A and P divides n. Because such prime existed, then of course these two numbers won't be coprime either. And similarly for B. So, so what it means that if this was invertible, these two elements are invertible. So f at least exists. Okay, so the next question is whether it's a homomorphism. And let me not check that that's, so f is a homomorphism. And I don't want to check that, but you can do it on your own. That's very simple. So you just multiply two things here, and now you want to look at the remainder mod n, and you just multiply remainders mod n, and you can just write it down, and this will be obvious. So obvious. And to be honest, the fact that on one hand you can do this with abelian groups, on the other hand you can do it with units, that's just a part of the statement that there is a homomorphism of rings, but we have not yet talked about it. Map which sends product to product, sum to sum. That's why this is also a homomorphism. But this is an exercise. So what else do we have to show? So the next statement is identity, so kernel. Let's compute kernel of f. So kernel of f, and so let's suppose that A went to 0. A went to identity, and this will be 1, 1. And this means that, okay, so A is congruent to 1 mod n. So it means a minus 1 is divisible by n, and a minus 1 is divisible by m. But then you can just, since n and m are coprime, you know that you can, a minus 1 is divisible by nm, so you can multiply. So we get a map which is homomorphism and injective, and the last question is why it is surjective. Okay, so surjectivity, the last thing to check, and this is the most interesting one. So let me explain that. So f is surjective. So let's just reformulate the statement. So the statement is as follows. So we have some pair of elements here. So let me denote it by, let's see. So let's suppose I have A1 and A2, two classes here. And my question is to find A here. And so let me now formulate what we need to show. So A1 is coprime. So let me say differently. So we have two numbers, n1, n and m are n and m are coprime. And then we have basically we are trying to find A. So so we need to show that there exists A such that A is congruent to A1 modulo n, and A is congruent to A2 modulo m. So basically we know, yeah, and we want to find such A, and then of course modulo, yeah, and then we will take this modulo nm and it will work. So this statement is the fact that such thing exists is called Chinese remainder theorem. Chinese remainder theorem, and we will talk about it more next quarter. And let me prove it right now. That's not very hard. So n and m are coprime, so then we know that there exists a pair of numbers x and y such that xn plus ym equals to 1. Okay, and then let's look at the following number. Let's look at number A1 times m times y plus A2 times n times x. So that's kind of a trick, and I call this A. And let's see what A is divisible by. So modulo n, so A is congruent modulo n, so this we can forget, to A1 my, and my is congruent to 1 because it's equal to 1 minus xn, so it's congruent to A1 modulo n. But simultaneously A is congruent modulo m from here to A2 and x, and nx is congruent to 1, so that's congruent to A2 mod m. And we have found our A in this kind of fancy form. So this finishes the proof of multiplicativity of Euler's function and the isomorphism we wanted to show here. And again, so this is a part of a statement which is called Chinese remainder theorem, and a more fancy version will just say that this ring is isomorphic to this product of these two rings. Okay, so let's deduce a formula for the Euler function from that. Okay, so let's take n equal to p1 power alpha 1 pk alpha k, where these guys are primes, distinct primes. So then phi of n equals to phi of this p1 alpha 1 times pk alpha k. And by multiplicativity, we know that different powers are co-prime. So that's phi of p1 power alpha 1 times phi of pk power alpha k. And this we can compute. So this is p1 power alpha 1 minus p1 power alpha 1 minus 1 times pk power alpha k minus pk power alpha k minus 1. And here you should be careful. You need to assume these are actually not equal to 0 powers, otherwise you will get some nonsense. And so this can be also rewritten maybe more nicely as n times 1 minus 1 over p1 times 1 minus 1 over pk. So product of inverse primes contained in 1 minus prime contained in n. And that's the proof, but there are other proofs. I mean, one way to prove it is to use exclusion-inclusion principle. You kind of count all elements. So suppose n is divisible by p, you can count all elements divisible by p. And this is just n over p, p1. But then you cover all elements divided by p2 and so on up to pk, and you get basically that you need to subtract n. So by inclusion-exclusion principle, you get that this number equals to n minus n over p1 minus n over pk. And now you subtracted basically the number of all numbers divisible by p1, p2, and so on pk. But now you counted twice the numbers which are divisible by p1 and p2, and so on. And so you need to kind of return them back, and you get something like that, pk minus 1 pk. But then you start subtracting all triple products and so on, and eventually you get the same formula. So this is just, if you open brackets there, you will get this. Another way to think about it is that basically the probability that some number below n will be divisible by p1 is 1 over p1. Probability it's not divisible by p1 is 1 minus 1 over p1. And these random events are independent because these are different primes, and so you can multiply them to get probability that your number is coprime, which is phi over n divided by n. That's kind of another approach. Okay, so that's all good. So I want to give another kind of interesting application. So let's look at the group z over nz. So let's see. How many cyclic subgroups of order k? So we know that, so let's consider orders of elements here. So we know that order of element k here is equal to n divided by the greatest common divisor of nk. So in particular, you can easily see that a number of elements of order n, which is the same as number of generators of the group, is of course just equal to the number of coprime numbers k. So this phi of n. And okay, so you can look at number of elements of order smaller than that. So let's see. So what is the number of elements of order d? So let's look at the number of elements of order d in z over nz. And of course you need d should be some number dividing n, otherwise you'll fail miserably finding such elements. And the answer is that this is equal to the order function of d. Okay, let me prove that. So I want to erase that part first. Okay, so how shall I prove that? So that's very simple. So let's consider z over nz. And I'm interested in elements of order d. So let's look at a subgroup. So subgroup of elements of order d. So d divides n, and there is this map which, so let's suppose that n equals d times d prime, and there is this map from z over nz to z over d prime z, and this is just multiplication by d. So multiply every remainder by d, you will get a remainder by d prime. So again, we already discussed that map a few times, it's surjective, and the kernel of d, so it's a subgroup, is a cyclic subgroup, and the subgroup is definitely having order d, of order d, and so is isomorphic to z over dz. So these are elements whose order is whose order divides d. So this kernel are elements whose order divides z. And we want to elements of order exactly d, and it's really easy to see that these are exactly generators of this subgroup. So so now we are interested in so the number of elements of order exactly d are generators of the subgroup is equal to 5d, because it's also a cyclic group of order d. So basically we have this interesting statement that in a cyclic group, if you are interested in elements of certain order, you just compute Euler function of this order. So let's look at z over maybe 6z example, and we have here 0, 1, 2, 3, 4, 5 elements, and here we have their order, and 0 so 0 has order kind of infinity, it's 0, not interesting. This has order 6, this has order 3, this has order 2, this has order 3, this has order 6. And so there are 2 elements of order 6, 2 elements of order 3, 1 element of order 2, and indeed phi of 6 equals to 2, phi of 3 equals to 2, phi of 2 equals to 1. So all numbers add up. Very interesting statement. It has a beautiful corollary. So corollary is as follows. So you take sum of the values of the Euler function at all d where d divides n. So you sum function over all numbers which divide n, and the statement is you get n back. And this is obvious because you just have this cyclic group, you have all elements there are n elements, each of them has some order, and basically you just sum up phi of all numbers to get all of these orders. Yeah, sorry, 0 has order 1, what I'm talking about. So this is phi of 1 is 1. And that's why you need to also have 1 here. So that's a very beautiful property of Euler function, and we will use it later on. So last thing I want to say is that there is an interesting question. So we said that the z over nz multiplicative group is a group, but the question what this group actually is. And let's start with p, so you can take z over pz and look at it as a multiplicative group. And the question is, okay, which one do we have? Maybe it's product of cyclic groups, maybe something else. And you can experiment with that. So the answer is very beautiful. We will prove the answer, but probably next quarter, so not this quarter. But that's a very interesting question. You kind of need slightly more algebra to actually maybe prove it. So we can do it. And the proof will be based on this corollary, which I just mentioned here. Okay, so here we finished talking about this cyclic groups and Euler function and so on. And next time we will touch on a more advanced topic in number theory, namely quadratic residues.